it's Painlevé I equation and modular forms. It's based on particularly based on our joint result with Kyiv, Mykola and Yuri Zhurablov published last year. Okay, what is the Painlevé I equation? It's ordinary differential equation of second order. It's the simplest in the series of 6 Painlevé equations, and they were found by Paul Painlevé in the beginning of 20th century. He tried to understand how something about analytical properties of solution of differential equations and to classify them from the point of view of some property which is now called Painlevé property, is a property to find such equation having solutions without movable irregular singularities, like branching point. What does it mean? It means that if we change initial conditions for we may expect that if the solution has some poles, they can move, but if we have some branch points or essential singularities, they should not move. Probably it's, I don't know, from the point of view of differential equation, now it's strange, maybe this property, but in any case, he found 6 such equations which cannot be reduced to hypergeometric equations and so on.
Yes. The equation is ordinary.
Yes.
We would like to classify the equation in partial.
No. Only ordinary dictum.
Yes. Okay.
And is this first equation, we have some nonlinearity and second derivative. It means that generic solution should depend on 2 parameters. About information about Paul Painlevé, he's a French mathematician working in the differential equations, but he was also twice times Prime Minister of French Third Republic in 1917 and 1925. Before 1960, he was a professor at Sorbonne University, then moved to politics. Okay. About Painlevé I equation, it can be considered as a Hamiltonian system, for example. In this case, we should take the Hamiltonian dependent on time. If we take such Hamiltonian as written here and write Hamiltonian equations, then the equation of motion is exactly Painlevé I equation. But there is a dependence on time in the Hamiltonian, and it gives a possibility to write all the evolution of the system in terms of evolution of Hamiltonian. For example, to find the dependence on time of coordinate, it's possible if we know the evolution of Hamiltonian in time. We can just differentiate time and we'll obtain coordinates. Thanks for momentum. So we need we have some function like Hamiltonian. The momentum coordinate have some evolution with respect to equation of motion. So we have some dependence on time, and we can solve such type of equation. And in fact, it's better to consider some another function related directly to Hamiltonian, is related by some like differential logarithmic derivative, so-called tau function. Why the tau function is better? Because usually the solution in the Hamiltonian for coordinates have poles in time, but we consider time as a complex variable, in fact. So we consider analytical properties of the solutions in all the complex plane. It's standard way to consider analytical properties of differential equation in and its entire function without poles, tau function is entire function without poles, and having only essential singularity at infinity. And there is another story relating it to isomonodromic tau function of matrix linear differential equations with irregular singularities. And now, okay, I have one more slide about application of Painlevé equations. In fact, we know different type of applications to physical problems, like correlation function for two-dimensional Ising model, random matrices, describing new solutions of Einstein equation. And Sergei mentioned in the previous talk that it's possible to describe some models for DNA using Painlevé I equation. But subject of this talk will be some relation with quantum field theory. And I was involved starting more than 10 years ago when we observed that there is some relation, unexpected, with solution of Painlevé I equation, bit more difficult equation, and the conformal field theory, two-dimensional conformal field theory. And we tried to understand how to generalize this equation, this relation to another Painlevé equations. Okay, and the correct object to generalize is the tau function. 10 years ago, the group of authors found that the tau function of Painlevé I equation can be presented like Fourier transform of some unknown function. And as I said, we have second order differential equation depending on two parameters. Initial conditions should depend on two parameters. Generic solution should be dependent on two parameters. Here they are nu and rho. Rho enters like Fourier, parameter for Fourier transform, and nu is some other variables. And what is this z function here? In the case of Painlevé I, it was just conformal blocks, the correlation functions for two-dimensional conformal field theory. In this case, it should be something like conformal blocks, but of some unknown conformal field theory with irregular singularities. What is the structure of this? Just substituting such expression into the nonlinear equation, Painlevé I equation, we can find the expansion, and the structure is the following. We have some constant written in terms of Barth's G function, and some series in the variable s is more or less related to time. And we can try we plug into Painlevé equation and find explicitly some of these coefficients. And the question how to explain what is the meaning. So the main thing is that it's nonlinear equation, and we have in fact some explicit formulas, some structure with unknown polynomials and so something like this. And it was suggested that in fact this function z is just a partition function of some new theories, so-called Argyris-Douglas theory, namely, if we take free energy, we think that z is a partition function of this theory. We can expand in so-called topological expansion in H bar, and we obtain some functions like free energies. And the conjecture was that these two objects, one in Painlevé I equation, and this partition function of Argyris-Douglas theory is essentially the same object. Just for information, I don't enter into this. Argyris-Douglas theory is a class of effective supersymmetric theories with irregular singularities, and is initiated by Argyris and Douglas in 1995. So we have some unusual relation between theories, between classical Painlevé equation and very non-trivial theory, supersymmetric theory. We can check, expand, check all the coefficients, and but from the point of view of now it can be done by computer, but the main thing is to understand all these relations. But from the point of view of Argyris-Douglas theory, it's known that there is some structures related to topological string theories and so on. Probably they're not realistic or not realistic, but in any case, it's motivated many results in mathematics. And all these free energies can be computed by holomorphic anomaly equations, describing modular structure of free energies. And now I remind or explain some basic things about modular forms. It's a story about if we have non-Euclidean geometry realized on upper half plane, is so-called Poincaré half plane. The group SL2R of 2x2 real matrices with unit determinant act on the point of this upper half plane, and it's just some like motion of this upper half plane, conserving so-called Poincaré metric on it, non-Euclidean geometry. And there is some discrete subgroup. Is just constructed from integer matrices. This subgroup is generated by two matrices like T and S. One shift Z by +1, and another makes such transformation like here. And we have action of this discrete group on the upper half plane, and we can try to understand what is the fundamental domains which cover all this plane when we act by SL2Z. And this picture is known from 19th century. It's interesting that Painlevé was in Göttingen and working with Felix Klein that time, but I'm not sure that. And
Я тут
now
бабки.
all this stuff is related.
Подгорает уже.
Mhm.
Так.
Just a moment. Gamma is a discrete subgroup, this modular group. So the situation is, if we have translation on the real line, for example, and we have some discrete subgroup which translating by unit, for example, then we can consider function which respects this periodicity. So it's similar. We have similar picture for complex plane. We have translation on the complex plane, and we have some discrete group translating by some lattice of parallelograms. In this case, instead of
complex in time.
Just complex plane.
Complex.
And we have some translation in this discrete by discrete lattice of parallelograms, and functions which are periodic are so-called elliptic functions. There is some similar picture for acting of this modular group SL2Z on the upper half plane. We have many like curved triangles here, and they look like different in sizes and not triangles, not straight lines, but in fact they are all the same if we consider in Poincaré geometry, using Poincaré metrics on the upper half plane. So from this point of view, all these curved lines, circles, it's just geodesics in this geometry, and all these triangles are just the same, and we have covering both the upper half planes by these triangles. And modular functions are just like periodic functions with respect to such action of gamma. We need some more general objects like tensors with respect to modular forms, which of so-called modular forms of weight k. Their rule of transform is bit we need to correct to add some multiplier here depending on k, and if some function transforms like in this according to this rule, we say that it's a modular form of weight k, and they constitute as some vector space. So explicitly the action in this case for these functions like here, we have such property of periodicity when we move by +1, and it motivates to consider to make some Fourier transform with respect to Q, which is so-called a norm. And in this case, if this holomorphic modular form is holomorphic, we have such expansion in this Q. There are some examples, so-called Eisenstein series, which are defined as some generation functions for some number theory properties. We have here some Bernoulli numbers, and sigma functions is so-called divisor sum functions. It's for every integer n, this function is sum of all the divisors of n to the power j. And the property is that all these modular functions are modular of weight 2k, but this E2 is not exactly modular, but there is some correction for modularity. And the main property is that, in fact, we have not too many modular forms, in fact. And all the modular forms just are polynomials in these two Eisenstein series, A4 and A6, E4 and E6. And here we have the dimension for or the space of holomorphic these modular forms for different ways. And it means, for example, that if we multiply E4 squared, it will be E8 because we have only one-dimensional space for of weight 8 and so on. Already this relation gives many non-trivial properties for number theory. There is some special properties if you consider modular forms of weight 12. It's first case when we have two-dimensional space, and we can take difference of these two forms, and in this case the series in norm will start from Q, meaning that we have some zeros at infinity. And this idea allows to find some good basis in the space of modular forms. And about quasi-modularity of E2. E2 is also a good function, but unfortunately not modular because we have some correction here. It's possible to do it modular, adding some non-holomorphic part. So we have either two possibilities, or we have quasi-modular form, which is not just modular, or modular but not holomorphic because we added imaginary part of Z. And this E2 and E2 star are important in topological string theory and describe some holomorphic anomaly. It means that here we have some non-analyticity, so dependence not on Z, but only on the imaginary part of Z. And in some way, we can control all these anomaly in holomorphic properties using this function. And it led to some holomorphic anomaly equation written here. It's some like recursion relation for free energies. It's quite universal in for many theories, and in particular for Painlevé equation. And the only problem is that when we consider this equation, we have some ambiguity when we solve it, because it can be solved iteratively up to some constant term independent of E2. And it can be solved by requiring some properties that we have many zeros in the expansion of modular forms of free energies in terms of norms, as written here. For example, for the second order term, energy, free energy in Argyris-Douglas theory looks like here. We have some coefficients, and they can be obtained using only modular forms and so on. And exactly if we combine all these free energies obtained by this procedure, we obtain a solution of nonlinear Painlevé I equation. Okay, it's almost else of the story. So we have shown that holomorphic anomaly equation appearing some in topological string theory and so on can be applied for Painlevé I equation to fix free energies in topological expansion for Painlevé tau I function. We have some proof, but not direct, using topological recursion and so on. And we're planning to find similar relations between modular forms and Painlevé equations. Probably that's all. I just want to say that there is some modern story about we have some string theory about we don't know how is it realistic or not, but in any case it gives many connection in mathematics, and all this stuff shows that we have some new connection between modular forms and Painlevé equations. Both are classical subject in mathematics for more than 100 years, but there are new relations unexpected appears.
Thank you.
Sorry for too many.
Mykola, no, thank you very much. Would you please comment on the modular forms for Painlevé II equations, and then I will explain my interest to Painlevé III.
Of course, we have to adjust. So the idea is that we have to use some modular forms. The question modular forms with respect to another discrete subgroup. So there are many subgroups. All are important for number theory and so on. There are many books, but we need to understand which are important for Painlevé II and other equations. The answer is like some congruence group, two and so on.
Steve, the following bit. I collided with the Painlevé II equation.
Okay.
Many years ago when I was a newcomer in the nonlinear physics. Dissipation energy of the soliton, nonlinear cubic Schrödinger equation. But it appears when the velocity of the soliton is bigger than the velocity of the sound. So in some analytical area, which was considered as non-physical, but that was before the paper by Zolotaryuk and Davidov on supersonic solitons. So I think that there is something, maybe it is connected also with the analytical continuation into the area of the complex time because of the energy dissipation.
So from the point of view of integrable system like MKDV, modified Kardashev de Vries, for example, in asymptotic regions of X and time, the solutions are described in terms of Painlevé II equations. For Kardashev de Vries,
for Nobel Prize.
for Kardashev de Vries, the situation is asymptotic region is described by Painlevé I equation, and there is one parallelist story which I not mentioned, but all this, for example, Painlevé equation, one equation is describes non-perturbative corrections to cubic oscillator,
Yes.
quantum cubic oscillator. And Painlevé II equations describes non-perturbative corrections for quartic potential and so on. So
What it means unharmonic.
all,
That is
all, all the-
exactly the what I mentioned.
yeah, I think all things.
Complexity which
can discuss it.
admits the supersonic.
So now there is some interest because of new formulas which can be used, but by hands it's very difficult to use. But now we can conjecture, make a conjecture and verified by computer algebra experiments like to find different relations.
Thank you very much for your talk. And I have maybe not serious question, very simple for you. Why we have the coefficient states in the initial and the one equation?
Oh, it's just for historical reason.
Historical.
Yes, because in fact all the coefficients here are not important. We can rescale x and t, and
Yes.
we can rescale just partially historical, and some formulas are adjusted to these coefficients.
You should. No. I would like to make some comments to very specific about the about some historical and similarity of event after the velocity of Solton is higher than the velocity of sound. There's approximately after the the school developed, we have the idea the paper by Wilfors in Journal and he read the soliton not in the terms of coordinate and velocity, but in terms of coordinate and momentum. And in these two physical variables, there is no any singularity. Yes. No question. Yeah, and now question. I would like to return to my short question about the Painlevé equation that you have said to be ordinary equation, and that was these equations are classifying the nonlinear system also ordinary, but how it looks, how it is, I understand that after that we deals with the two-dimensional field theory. I suppose there's two-dimensional and fields, at least three variables should be involved in this equation. It's not ordinary equation. You see, explain this. This is very popular.
In fact, we have some special quantum field theories like four-dimensional with supersymmetry. Very difficult, probably. But if we calculate some things there, we have some parameters like coupling constant or something like, and it plays the role of time in this series. So there is not the direct relation between all these theories. So there is no problem with different dimensions of this. So in a sense, Painlevé equation describes something about dynamics of four-dimensional theories. It's very special theories. It's non-usual, probably for arbitrary theory to be described by Painlevé. So
some integrable, some
We have
some function of this.
So we can
Coordination function or something
yeah.
like that.
We can say that even that those theories like supersymmetric, they have some hidden integrable structures, one-dimensional somewhere, and we try to understand them.
And there's a historical remark about Poincaré that you mentioned.
Okay.
Of course, he was one of the leading mathematicians of his time. And in Sweden, we had a mathematician named Mittag Leffler. And Mittag Leffler, there is now an institute named after him in northern suburb of Stockholm. Anyhow, around 1910, I don't remember exactly, Mittag Leffler started an enormous campaign for Poincaré. Which you shouldn't do, but he did it. So there were nominations from Japan over Europe to United States for Poincaré, and he had, for a long time, he had a record number of nominations for 1 year. I think he got something like 38 nominations, which was a very high number at the time. Anyhow, the problem for Mittag Leffler was that his enemy, Svante Arrhenius, was on the Nobel Committee. And Arrhenius, of course, understood very well that this was a campaign started by Mittag Leffler. So I'm sure he did all he could to stop giving a prize to Poincaré. But he had a few supporters in the Nobel Committee. He didn't make it, and then he died, so it could not be. But this was Mittag Leffler's enormous campaign.
Thank you. It's interesting. I just read Wikipedia. I not found some relation between Poincaré and Painlevé.
No.
I don't know why, because Painlevé has some contacts with Felix Klein, which was that time how to say
Right.
with Poincaré. Also, Painlevé made some talks in Stockholm, like serious lectures at the end of 19th century, like 1895 or something, about singularities, but for n-body system. So it's also some topic related to three-body system and Poincaré, but there is no mentions, about Poincaré and the relation, and some. And probably both were in politics in French.
Yes.
But probably it's related or not. It's explanation. Okay.
So Alexander,
You mentioned the relation of Poincaré and its solution of Einstein equation.
Yes.
In which what I mentioned.
Usual for dimensional, some special like generalization of Schwarzschild solutions, but for special, more special solutions. In any case, it's some restrictive solutions, but
And the second about topological streams. Would you explain it very short?
it's difficult. I don't possible, I think. I just know that there is some relation for instead of initial four-dimensional supersymmetric Young-Mills, Zyberg-Witten considered some effective theories and
Logical means expansion in general.
at least. Okay. Okay.
In Zoom.
So the last question. The last question is as follows. Is it possible to give some ways how to generate new integrable nonlinear systems related only by the vector? Yes or no?
I don't know. Okay.
At the end of our session. So, from myself.
Yeah.
So, we are grateful to organize our speakers, especially our.
Там питання.
There is a question from Eric.
Yeah. Yeah, thank you. I mostly wanted to say thank you to a talk, but it's a bit far from my expertise to really ask a factual question. Though I should point out, when I was in Kyiv last time, I heard there were several people working on this in the math department. I mean, on automorphic forms and modular forms and related stuff in one of the new universities in Kyiv. So my question is, do you have some interaction with local mathematicians
Yes.
also on this?
Yes, I have a joint project with Masha Vlasenko.
Yeah,
by
okay.
National
Yeah, of course, yes.
Already have. So
Yep.
thank you.
Okay.
So thank you once again. Send to our Swedish colleagues, to listeners. Have a good day.